Lesson 3 provides an overview of VMware NSX logical switching. This lesson covers the following topics: traditional Layer 2 or Layer 3 networks versus VMware NSX logical switching, VXLAN overview, VXLAN Tunnel Endpoint or VTEP, Transport Zone, Logical Network, and VDS, VXLAN Overlay Tunnel, VXLAN Frame Walk. Today's cloud computing architecture supports multi-tenant by definition. Each tenant requires its own logical network, which in turn requires its own network identification. Traditionally, network engineers have used VLANs to isolate applications and tenants. However, VLAN specifications only allow for up to 4,096 network IDs to be assigned at any given time, which is not enough for a large cloud computing environment. Traditionally, for a virtual machine to migrate, it requires that you build huge Layer 2 network domains. In a large Layer 2 network, spanning tree protocol convergence can take long and is hard to manage. The requirement of Layer 2 everywhere is difficult to accomplish. NSX logical switching is based on the VXLAN protocol. A logical switch is an L2 Ethernet broadcast domain that is implemented using VXLAN. The VXLAN-based virtual Layer 2 network is abstracted from the underlying physical network. One of the advantages of VXLAN over VLAN is that VXLAN increases the number of available logical network IDs to 16 million and allows for Layer 2 adjacencies across underlying IP networks. Millions of isolated Layer 2 VXLAN networks can coexist on a common Layer 3 infrastructure. Deploying VXLAN is a key to building logical networks that provide Layer 2 adjacency between workloads, virtual or physical. VXLAN helps you move to a software-defined data center model. It allows an administrator to provision a virtual machine that can communicate with another virtual machine on a different network without having to configure the physical switches and routers. VXLAN is also helpful in other scenarios. Assume that you have a cluster with a given set of VLANs assigned, and these VLANs are not shared across other clusters. However, you have the requirement to place virtual machines across those clusters. To accomplish this, you can use VXLAN logical switches to cross Layer 3 network boundaries. VXLAN runs over standard switching hardware and has been embraced by most vendors. The deployment of overlay technologies has become very popular because of their capabilities in decoupling connectivity in the logical space from the physical network infrastructure. Devices connected to logical networks can leverage the entire set of network functions, independent of the underlying physical infrastructure configuration. The physical network effectively becomes a backplane used to transport overlay traffic. VXLAN stands for Virtual Extensive LAN. It has become the de facto standard overlay technology and is embraced by multiple vendors. Deploying VXLAN is the key to building logical networks that provide L2 adjacency between workloads without the issues and scalability concerns found in traditional L2 technologies. VXLAN is an L2 over L3 encapsulation technology, crossing Layer 3 boundaries. The original Ethernet frame generated by a workload is encapsulated with external VXLAN, UDP, IP, and Ethernet headers to ensure it can be transported across the network infrastructure interconnecting the ESXi hosts. The VXLAN, UDP, IP, and outer Ethernet header add up to 50 bytes to the encapsulated Ethernet frame. Scaling beyond the 4,096 VLAN limitation on traditional switches has been solved by leveraging a 24-bit identifier, named VXLAN Network Identifier, or VNI, which is associated with each L2 segment created in logical space. The 24-bit VXLAN Network ID field allows for over 16 million logical networks. Each logical switch is assigned a unique VXLAN numerical identifier, or VNI. Each logical switch is created as a port group on the distributed switch. Logical switches can extend across multiple distributed switches. The displayed diagram gives you an example of VXLAN-based logical networks. There are 3 physical hosts, with each as its own IP address. There are 5 virtual machines residing on these hosts. There are 2 logical networks configured on the distributed switch across the 3 hosts. The web tier virtual machines 1, 2, and 3 belong to logical switch 5001. The application tier virtual machines 4 and 5 belong to logical switch 5002. A transport zone defines a collection of ESXi hosts that can communicate with each other across a physical network infrastructure. This communication happens over one or more interfaces defined as VTEPs. A transport zone controls the hosts a logical switch can reach and can span one or more vSphere clusters. A transport zone extends across one or more ESXi clusters and commonly defines a span of a logical switch. The transport zone dictates which clusters and virtual machines within the clusters can participate in a particular network. The relationship existing between the logical switch, vSphere distributed switch, and transport zone is central to this concept. A vSphere distributed switch may span multiple ESXi hosts, and it is possible to dynamically add or remove single ESXi hosts from a specific vSphere distributed switch. In a practical VMware NSX deployment, it is very likely that multiple distributed switches are defined in a given NSX domain. The figure on this slide shows a scenario where a compute VDS spans across all the ESXi hosts belonging to compute clusters, and a separate edge VDS extends across ESXi hosts in the edge clusters. The transport zone defines the VTEP members of the VXLAN overlay. As you can see, a transport zone can include ESXi hosts from different vSphere clusters. A cluster can also be a part of multiple transport zones. As an administrator, for security or compliance reasons, you can create a separate transport zone that includes a dedicated cluster or clusters. A logical switch can extend across multiple distributed switches. As indicated in the example on the slide, a given logical switch can provide connectivity for virtual machines that are connected to the compute clusters or to the edge cluster. A logical switch is always created as part of a specific transport zone. This implies that, normally, the transport zone extends across all the ESXi clusters and defines the extension of a logical switch. One or more vSphere distributed switches can be part of the same transport zone. A given logical switch can span multiple vSphere distributed switches. When virtual machines on different hosts communicate, a VXLAN overlay is established between VTEPs on both hosts. In this setup, VM1 is on host A and VM2 is on host B. Both virtual machines belong to the same logical switch. When the two virtual machines communicate, a VXLAN tunnel is established between the two hosts. The VTEP on the source host handles the encapsulation of each Ethernet frame. Encapsulated frames are forwarded normally on the IP network. The VTEP on the destination host decapsulates the frame. The virtual machines send and receive standard Ethernet frames. They do not see the VXLAN ID or the underlying physical network. The VXLAN overlay tunnel is completely transparent to virtual machines. Now let's take a closer look at how frame flow works. VM1 sends standard Ethernet frames to the local VTEP on host A. The VTEP adds VXLAN, UDP, and IP headers to the original Ethernet frame. The physical transport network forwards it as a regular IP packet. The destination VTEP de-encapsulates the frame and sends the original Ethernet frame to its destination, which is VM2. Which of these statements are true about